pairs of protein interacting. I showed you that the interfaces differ between protein inside and outside. And that we talked about this issue of statistical significance versus scientific meaningfulness. And let me just repeat this. Sorry, did I show you this graph already? So this is a very important graph. What it shows here is the number of babies born in one particular region in Germany over the year. That's the publication. And you know what I'm going to show you next, right? Now I'm going to show you the number of storks born in a given year. And you absolutely see an absolute, at least it is from these data, it's very clear that in Lower Saxony, the north of Germany, the storks bring the babies. Clear correlation. And this is just one of those things to put it back into your head. Seeing a correlation does not mean that there's a causative effect. But what does it then mean that interfaces differ? Does it mean that there's a different biophysics? Does it mean that there is underneath a causation? Or is it just a correlation? Well, one thing is clear. If we can predict that this is a particular interface between two proteins as opposed to inside of the protein, if we can set up a system that can actively do it from scratch, then there must be causation. Then there must be some reason. This is no longer a correlation, in some sense. And that's what we can do. In fact, we can even, and here comes the next point to causation, we can learn something about the biology. The system that predicts the interface type can even identify hotspots. Hotspots are the residues that are carrying most of the energy of the interaction. And we can do that without putting into the system ever the idea of a hotspot. In fact, there has been a long debate. Do hotspots exist? So hotspots, again, the idea is maybe 50 residue make two proteins bind. You take one residue away, and half of the energy of binding is gone. So one of the 20 carries much more of the power of the binding. And that typically is called a hotspot. Now, the reason why this was a debate, are there hotspots, are there not hotspots, essentially is the argument the people who argued against the existence of hotspots argued, well, there's a gradual change. This may not be linear. It may very well be that there is a sort of an exponential. If I plotted here the percentage, that is 1, 2, 3, and when we go to 20 here in a typical interaction, and that's 100% of the binding energy, then the first may carry much more. This is an exponential type of function, but that does not mean that there's anything specific to number 1, or the first 2, or the first 3. It's just the spectrum. Right? That was the experimental debate. And you can immediately see that this argument makes a lot of sense. So, in fact, that is also why it's so difficult to experimentally make the point there are hotspots. But here, I come up with I take the experimental data after I set up my training device, and I come up with a classification, and the training device can see the difference between hotspots and not, although it never had a notion of hotspots. If a prediction device can see that, then that lends credibility to the fact that there is a difference between the first few and the others. And that also gives you a clear idea, this is not just a correlation of the babies in the storm. There's a clear causation here. And this is a beautiful example for how machine learning really tells you something about a system, tells you something about the biology. How machine learning allows you to see something that no experimentalist could clearly see. Funny enough. By sort of turning the problem around and looking at a completely different aspect and trying to predict something, you learn something else. And on top you developed a prediction method. That was, for us, the original reason why we did it. Now, in principle, this is great. And this is prediction is the acid test for understanding is often the idea. But machine learning has this problem of being like black magic. And that is because somehow it does its thing, but it's hidden why it does it. And I'll get back to that in a minute. In order to do that right, machine learning, you have to really work on the way you test. One way, this is just one particular machine learning device here. The idea of the picture simply is there is some data that you use for training, and some other data that you use for testing. And while you train, you have to somehow hide this training data under the table. Now, in more detail, it looks like this. You have the entire pie here, 100% of your data. You slice it, in this particular case, you quarter it, and you train, and you test, and you have machine learning. And that's the right way of doing this. Is that all? Yeah?
Why should we hide the train set, the test set?
Why should we hide it? So the idea is essentially, you hope understanding means the machine learning device takes principles out of the data that you don't know. Does it really do that, or does it take something that sort of is just in the data set? And in order to answer that question, you have to take out a subset of the data, and that is like, in some sense, it simulates the future data that you do not have today. And then you have to see whether for that subset you really can perform the task, or whether you can only perform the task for what you directly see, what you train on, what the green part is here. If you can only do it for that, you may not extract any rule. You may just learn the data by heart, so to speak. Can you extract a principle, an idea, a concept? Do you actually get some sort of implicit understanding? If so, then you can do it for a new data set. Then you can do it for anything you will see in the future. You don't know what you will see in the future. You simulate the future in some sense by taking a subset of today. And you have to hide it under the table, because otherwise you never know. We are all people. And maybe there is something that I learn from this training setup. And maybe that something is specific to the green set. So I better hide it for myself. In that sense, I really mean hide it. But now the next question for those in the room who have done machine learning, is that enough for doing a typical straightforward machine learning cross-validation test? What is missing? If you said no, I'm not entirely sure to interpret the circular movements of your head. Sometimes they say like no, and sometimes you say just.
So it's not enough because for cross-validation you need a third set. You extract from the train set.
You go ahead. You go. Oh, I have to change that slide. You're ahead of me. The first thing you have to do, and you're right about that. I'll get back to that in a minute. But the first thing you have to do is you have to repeat that. And the reason for that is that this particular test set you picked on, by coincidence, could have been the easiest. Now, the way you repeat this, in fact, you have to do it many times. Many times, you could imagine that you simply randomly choose subsets. But that's not a good idea. In fact, you have to do the rotation such that every single protein in your data set is used as a test set exactly once. No oversampling, no undersampling. Provided you believe that today's data is the best representation that you can possibly get today of tomorrow's world. If you believe today's data were biased, you better do the redundancy reduction before you do the rotation of these data sets. Right? Such that you end up with what represents for me here the entire pie, which is the data set that you believe is the best sample of what you believe tomorrow will be like. You know it will be different, but you have to do the best you can do today. And that is what symbolizes the pie. And that typically means redundancy reduction. It typically means get bias out, and we'll get back to that in a minute. Now, the next issue is that enough? And again, David will come in a moment, but there's something else missing. And let me illustrate this in this particular example here. So, say you had method number 1 trained on some features, and you get that. That is your performance. Method 2 trained on features, but a slightly different machine learning device. And method 3, different features, different machine learning device. Those are the levels of performances. The conclusion is that method 3 is best. Oh, I don't know what I did. Method 3 is best at performs at 37%. Is that right? Before you can write that in a paper, do you have to do anything else? Again, David made a point, we will get back to that. That's not the point I mean. Does anything else come to your mind?
Maybe have some error measurements on.
Absolutely. So clearly we need two things. We need an error measurement, so we need to see whether 37 is a substantial difference from 34.
And usually do compare it to random as opposed to...
That's this part, exactly. You have to essentially, in some sense, the error difference also has to do with how far away from random you are. If your error is in the proximity of random, you can no longer make these points even if the error is clear. Or it gets more complicated to make that point. So one is random, one is state of the art. You have to try to see what other methods people use for that task today. Or is there a competitor out that does exactly the same thing? In some cases you do a new method, but then the question really is, what do the people use today? And can you compare yourself to them? And if you used state-of-the-art methods that do exactly do the same thing, have you tested it on the same data set? Or have you just taken their published level data and copied it to yours? That's apple and oranges. Sometimes you cannot avoid to do that. Sometimes there's nothing else you can do. But then you have to mark it in a way that's very, very clear that you compare apples and oranges. Typically the way to do that is don't put it into the same table, to make it as difficult as possible. And at the same time, don't hide from readers that this is the case, but make the point that this is not a clear comparison, whether it works to your benefit or not. And then the standard error, we talked about that. Now, assume the standard error would be like this. So in this particular case, there's 1 plus minus 1 percentage point. And by the way, the rule of thumb really is to state that you take the standard deviation, square root of the number of samples, gives you roughly the standard error. And so say these were the numbers: random 32 plus minus 1, the method 3 plus minus 1, 37. So clearly within one standard error, this would be better than random, and it would also be within one standard error, appearing to be slightly better than method 2. But there's the next problem, and David put his finger on that problem. And that is that if you did this step now, if you concluded what I just concluded, these are the values for the test set. These are the values you took from the hidden away. The data that you get for training is relevant only for you as the developer. You learn something about, did you ever learn the problem? You learn all kinds of things about it. The world doesn't want to know how well you did for the training set. That's an overkill. What do they care? They want to know how that method works in the future. And the future is the test set. That's exactly what I showed here. That's the average over the 4, what I showed you before, the 4 rotations. In fact, my average is done on a per protein or per residue. How we compile this average is in itself a new discussion. Let's not get into that. But the major problem is another one. By arguing method 3 is the best, I use the test data. And the idea of test data is I cannot use it for making any decision. Okay, saying this method is better than that is only one free parameter. But it is a free parameter. It's part of machine learning. It's part of setting up a method. It's part of the stuff for which I should never use the test set. Therefore, in fact, I need 2 tables. And that's the point David made. Here, I show a particular way of splitting. You can split in different ways. Now, what effectively is left of my training set is only half of its original size. I take a quarter away for cross-training and take a quarter away for testing. Cross-training, that can be all kinds of things. It can be, for instance, what I showed you before. So if I had done this same table here on the cross-training, then I could say, in fact, method 3 is the best. I take method 3, publish, and in my publication I use the test set, but in this publication of the test set I say method 3 is the best. That's part of my cross-training procedure. Any parameter that I can fit, I fit in the cross-training. Okay? That is, for instance, choosing the kernel function. That is choosing the machine learning device. Is it random forest? Is it an SEM? That is, for instance, choosing the input features. In a particular setup of a neural network, that would imply the speed of training, the number of hidden units, and. All of these free parameters are chosen on the cross-training method. And you immediately see that this is a challenge, because it reduces the data in a world where you typically short data. Not only that, it requires that you redo the same thing again and again. So it's just an overhead in terms of CPU you need, personal time, and. And then you, again, as before, have to rotate completely through. such that in the end, every single protein, in the case of proteins here, has been used for testing here exactly once. I talked about that. Typically, in the world of proteins, we have a clustering of protein families. So my data here, I take all the green ones, the dark blue ones, the light blue ones, and the reddish kind of proteins. I put them all into one cluster, and then typically use one representative of each cluster for training and testing. So in my set, in my split, in this particular example here, it would in fact have only 4 proteins to start with, effectively. Now I could still train on all of these, but I cannot choose any orange when I train on a red. So when I use my test, then it must be from one of the others. Sometimes it helps to put the redundancy back into the training set, simply because you don't have enough data. But never put it back into the test set, and always avoid that there is an overlap between training and testing. This, in fact, typically is not even enough. Typically, still what you want to do is exploit pre-release data. What I mean by pre-release data is, at some point you're going to begin working on your thesis, on your work on this method. At this point you will collect the data. It will take some time. Some of the projects that I talked about, so this one here, that the next slide will show, here in fact took 3 years. From the moment of gathering the data to the moment of having the first method that worked. In 3 years, there was new data added to the database. And you could simply family cluster, so make sure that the new data, in fact, is not, so that's my old and that's my new, but that the new really is here. And then simply run your method on those new data that is not similar to what you had before. And that is a perfect way to give you an additional idea whether you're right. If performance here is better than you expect, you're lucky. You will not change your performance estimate, but you will be happy. If on this one here, performance will be much lower. I'm a little bit behind, and we do record because the lecture got filled.
Oh.
But we're getting close to the point that I can make.
Stay at second.
So, if your estimate of performance turns out to be utterly higher, so you did all the cross-training, you did the testing, and you get a performance P, and on the new data set, you get a number much lower than P. Maybe you want to, you clearly will report that in your paper. Maybe it's bad luck. So now we get back into the error estimate. The next question really is that within the error estimate? If so, fine. If not, well, check out what you did. But this, again, is a great way also to compare your method to other methods out there. Because they are published. So they also didn't have their fingers on those data yet. And that typically is a good way to compare your method to other methods. Now, if we have done all of that right, we can predict. The question now is, do we really understand? Or do we still have this issue that it's a black machine and we cannot open that black machine? That is typically what those who don't like machine learning attack. There's black magic and lack of understanding. And I'm going to talk today about a few examples that are showing how machine learning can be very scary and how it can go very wrong. But other than that, typically I'm a very believer in machine learning. And I don't take this argument. Here is why. Let's look at this. I showed you before the data. What it actually is I take the amino acid composition of a protein, and I ask, can I distinguish between different types of proteins? In blue, you see points for extracellular proteins, and red for cytoplasmic, and in green for nuclear proteins. This is a projection onto the first eigenvalues. Each eigenvalue here gives a value of minus 0.4 glycine, minus 0.35 N, and so forth and so on. That vector is defined, so again, we have the input we have 20 vectors, so we have 20 amino acids. Every one is a composition in that particular protein, and they span these vectors here. Reading these numbers you can plot these letter plots. And these letter plots suggest that you understand something. They're very intuitive. And in this particular case, where we have a very coarse-grained piece, where we have 20 input units, this indeed tells us something. It's a little bit more complicated what this one tells us, but it's related. And this is a way to, this is not really machine learning, it's fitting in one parameter. You do an eigenvector decomposition. It's very, very trivial. And you can, in fact, since the problem I start with is so simple, I can deduce something that suggests understanding. I can say that positively charged residues are absent, for instance, in extracellular proteins. And I can observe that the two positive charges here are more presented in nuclear proteins than in any of the other classes, and so forth and so on. That does not allow me for one particular protein, when I see a certain composition, to predict what it is. But it gives me a probability, and it gives me some suggestion why this could be the case. But this is only because the problem is easy. Now let's look at the problem that is a little bit more complicated. In this particular case here, I have the input being 20 consecutive residues, or 20 amino acids. One of them here is dark because it's the proline, meaning that at this particular position there's a proline, and then I go 5 residues to this end and 5 residues to that end, have a window of 13 consecutive residues, 13 times 20, plus I could have some additional information. So, can I, once my neural network, for instance, predicts that this is a residue, the proline here is in a residue that binds other proteins versus in a position where it doesn't bind other proteins, that's my prediction device, can I extract the rules from the system? And the answer is yes, I can. The problem is, what I find out is not going to tell me anything that helps me. The rules that the system learns are so complex that we don't understand them. That does not make them wrong. It also doesn't make them helpful. It also does not mean there is no understanding or there is understanding. One thing is clear, the machine learning device understood, if it can predict. I cannot get the rule out because what it understood is complex. So I stumbled over this the first time when I predicted secondary structure. For secondary structure, and in fact this figure comes from those, is over 20 years old, comes from the fact that a proline is a residue that typically breaks a helix, meaning that it is at the end of a helix. So it's typically when you have a proline, the helix that sits in a helix, the helix ends with that proline, typically the last residue in a helix. And I made this slide because my device did not predict that. And my method that in fact was better than anything that existed before was right. Most prolines in the data set did not break the helix. It was one of those simple rules that makes a lot of sense, biophysical sense. And we see many of examples that live up to that rule, but it's not the statistically significantly most dominant thing to see, or at least even if it is the majority thing to see, it's still not the best rule to use if you want to have a good prediction device. It's the best rule to use if you want to have a simple prediction device. But if you want to improve over simple, you have to do more than that. In that moment you touch rules, in this particular case, that you no longer understand. That does not mean you don't have understanding. That means that the way structure is formed, function is formed, is by principles that are not accessible to our simple ways of phrasing them. Maybe there are rules out there that we could understand that would be simple, but we haven't discovered them yet. The fact that the machine learning can do it, that it is a black box, does not mean that there is a simpler way out there that does it equally well, that suggests understanding. We have to always see whether the performance of the simple rule and the machine learning device is equally good. Okay? Okay. The problem here really is that when we write the rules, we don't understand them. Now let's get back to the prediction of protein pairs. And that is exactly the issue where machine learning problems blow into our face. Again, what we want to predict here is that this dark blue binds to the others from sequence alone. So in principle, we want to use some features that are derived by this predict protein, and we want to somehow see that's from one protein, that's from another protein, those two residues bind. We may not really predict the binding, but we want to predict that two proteins bind. That's the first step we want to do. And we have done many, many, many steps to get there, and I'm going to skip them now. The first problem here, so there is a particular challenge that comes from protein-protein interactions. The first challenge has to do with redundancy reduction. So before, we have a very simple situation. We have a family of related proteins, we put them into one bin, and we reduce redundancy by picking one from each of these circles. For protein interaction, the story gets a little bit more complicated, because now, in fact, what is in that bin here is not a protein. It's an interaction between two proteins. And this light green interacts here with the dark green, and the light green here interacts with the black or blue. Does that mean they're related? How should I cluster? Should I cluster by these original binding partners? Or should I cluster by interaction types? Comes a paper from Yongki Park and Edward Marcotti, and that says that we have three different cases. Case one, that the two proteins here in an interaction here have been used for training, but not the interaction. Okay? I'm not going to use in the test case this interaction, but what I'm going to use is green binds to yellow and purple binds to black. Not the interaction between these two. So that's case one. Case two is that one of the two has been used for training. So, for instance, green binds to yellow, not the purple one. But again, in none of these cases the interactions have been used. And the case three is that none of the two has been used for training. And the finding is that the methods that predict the pairing of proteins, in fact, reduce performance down here. So another example shown here a little bit, those are simply two methods, that is recall versus precision. Green for this method are cases that have not been used for training. Again, not the interaction, but the single players, the interacting partners. And red, they have been used for training. Two different methods, so the difference is slightly different. So here, red is much more different from green than here. But in principle, for both, you clearly see that red and green differ, and red is clearly above green. So whether or not the binding partner has been a part of the training set or not is crucial. And that is remarkable in many ways. Why should it? The interaction has not. Okay? And in fact, so what I'm hiding here, those are the plots from Tobias, and what I'm hiding here is not only the protein A and B, but also their homologs. So everything they are related to is excluded or is not excluded. Now the next question is, we train on negatives and positives in typical machine learning, where positives are two proteins interact, and negatives are two proteins don't interact. Okay, let's hold there for a second. How do I have some experiments that tell me that two proteins interact. How do I get the information that they don't interact? Do you believe that's in the same experimental database? Do you believe people have experiments of no interaction?
You can see if the test fails.
If the test fails?
You said
we're talking about experimental data first.
Yep.
So one step back. I have a database of proteins that are observed to interact. Now my question to you, do you believe that it will be equally easy for me to get an experimental data set of proteins that don't interact?
I think the easiest assumption is to see what data do I have for the interaction and just conclude for the others they don't interact. Because I don't think it's easy to get it.
Why not? Why would there be a probabilistic difference in finding the literature for interaction and non-interaction?
Because you will miss some data. So
Exactly. That's one reason. There's a social reason for that. If you find out that two proteins interact, and if one of those is important for a disease, that makes a difference. If you find out that any two proteins, and one is related to a disease, don't interact, who cares? So I have something that's very important for the mad cow disease, and I have something that has nothing to do with it. Hello? That's a great publication, huh? And that is, there's a variety of reasons why finding negative data is not easy. It's also not encouraged. But ultimately it's not encouraged because the problem of making sure that in order to say they really don't interact, you have to test many, many conditions. In order to say they interact, you have to have one condition. At least. Because then you can prove, in principle, they interact. All right? So then the only way out of that problem for machine learning is you say everything that has not been observed to be a positive is a negative. Exactly the way David suggested it. Of course, it's a hack. And now, the question becomes, we have this clustering, the redundancy reduction. Should we do that on the positives, or should we also do it on the negatives? Well, how would we find out, right? First we would Google, and we would simply see what does the literature say. And the literature says nobody ever considered it. So, that's a good proxy for saying it doesn't matter, right? What better thing can you do? Typically that implies that it's not relevant. What this one shows here is the difference between sampling or also putting the sample into negatives, yes or no. A positive difference means that between constraining the negatives and not constraining the negatives, there is a difference. So this is called improvement because it's not really an improvement. If sampling the negatives, constraining the sampling of the negatives makes a difference, then we should constrain it. And what is called improvement here is simply a mistake of not having realized that sampling the negatives makes a difference. In that sense, the word improvement here is misleading, but clearly it's a difference in the precision. And the difference in the precision is valid for most methods. There's a longer reason why it's not valid here, and essentially for lower recall is most valid. Lower recall means, so when an experimentalist wants to test an interaction, typically they test relatively few. They want your method to give them some highly reliable information for some proteins. So typically you are in that realm. So typically where your method is interesting for experimental collaborators, where you see most of the difference. So it really does matter. That means we have to absolutely also consider the negative PPI protein interactions. And that now is my original network of protein interactions. This is one particular protein, and ultimately it means that I have to throw away a lot in the way I choose the training and the testing set. And in fact, all of this choosing, so what for normal data sets is very simple. Redundancy reduction, find similarities, throw away everything that is too similar to each other. Now becomes a real problem. Real problem, you have to carefully choose the data sets. Now, that also implies that as soon as you put in some of these connections suddenly by adding data, your whole system tumbles. You can no longer use the same data set. One new measurement could sort of invalidate, in some sense, part of your data. That's horrible.
You have to choose between one interaction here. For example, looking at you try to have edges which don't connect nodes, but how do you choose the edge in the end? There are many ways.
So how would you do that?
Probably maybe choose, train, and choose again. So
that has two problems. One problem is personal time. Okay, our time is very limited. Any other problem that anybody sees immediately for this? Do you see one?
Then what are you going to choose then? One that performs best?
Yeah.
And you introduce the bias.
Yeah, that's the point. That's exactly the point. So Jonah's point is a different one. Because you would reduce the bias by choosing the one that performs worse. But that would be so stupid, right? So this is a subtle situation. It's dangerous to do. But I'll get back to that in a minute. In some sense, most conservative way of doing it is if you had another criterion for the better data point. It could simply be you have two protein interactions, and one you have seen in 5 publications, and one only in 1. Then you choose the one. If you could distinguish this could be an additional indicator, and it could help you to be less scared. And in fact, could help you to argue that is the right thing to do anyway. And that is the next challenge we get into. You open the door to exactly the next problem. That is the data, or other data. Typically, certainly in biology, but in many, many machine learning tasks, you will not have enough data to sample the world from tomorrow. We will typically have a data shortage. That typically implies you will try everything to use all the data you have. How much data is enough for machine learning? When do you know that your data is enough? You have any machine learning task, whatever it is. How can you figure out whether what nature gave you or what your supervisor gave you is enough for the task? So let me pop the first bubble that some people may have in their heads. Nobody jumps up and brings it, so I have to do it myself. So one idea could be, say, random, whatever that number means, I don't talk about it now. Random means 30%. And the fact that method does 35, you may argue, well, I'm so close to random, or let's call it 40, I'm so close to random, so hence my data are not enough. Is that right? Could that be right? It could be right. But is that clear that it is true? What else could it be? What else could be the reason why your method does not perform that much better than random?
I think you also have to consider the error again. So.
Sorry, thank you. I forgot to tell you the error is this. And now? What do I learn from the error for this? So back again, the question is, what could be the other reason that has nothing to do with the data, that's insufficiency of the data, that would explain that I cannot do more than 10% better? Yeah?
Because that's the error in the experimental data you're training on?
Yeah, but that is exactly what David suspected, right? That's why he wanted the error rate.
Maybe.
No? Yes, well,
you can get the error from the machine learning.
I'm sorry. And, you put your finger on it. There is a point to what you say, but you're pushing me a little bit. I gave you the wrong answer. You got a point there. But there's something more problematic, more clearly here.
Maybe we have wrong.
That's what these gentlemen, ultimately he clearly was after, and I suspect you may have been after the same thing. No, the point is that the machine learning device uses some input space. And this input space is just not solving the problem, as simple as that. Maybe the input vector is too small. Maybe it doesn't, the problem that we're talking about has nothing to do with local information. Maybe I'm trying to predict whether a protein binds another protein. Maybe this is decided by some environmental factor that I don't see in my input. So this may also tell me, it may tell me many things. It may be telling me that the data is not enough. But it may also tell me that in fact the way I address the problem is insufficient. That I don't have all the input I need, that I don't have all the bits and pieces that I need in order to predict. So, yeah?
So it's a computational problem? I don't understand.
now we get into lingo. I don't like to answer your question because the problem is the problem is not well defined. The machine learning is supposed to map one space, the input space, onto another space and classifies 2 points. As a physicist, I would argue the problem is not well defined. And now you could call that a computational problem, you could call it a lack of understanding of the problem, you could call it a lack of data, you could use all types of words for it. The point is, this may not be a problem of insufficient data. It may be a problem of the insufficient use of input. It may be that I needed to, so this does not mean that I don't know all the proteins that bind, but maybe I need also to know the time of the day that they bind. Or invent your own way of doing it. That does not mean that the data is not good, okay? Or that I need more data. It's just I need something else. I need to address the problem in a different way. That may also tell me that. Back to that question here. How can I answer the question whether or not the data set is the culprit in a typical machine learning environment? Think about something simple. Anybody? You halve the data. You simply throw away half of the data and see whether you can do it equally well. Or you throw away some percentage. If you can do it equally well between 100% of the data that you can use for training and 50% of the data, then you have some indication that the data may be enough, or we get back to that problem here. That you really don't have a good way of solving the problem. If, however, you see that between using half the data and using the entire data, the accuracy goes up very much, then clearly you need the full data, and you have this sort of suggests this, the degree of change here. You could use 1/4, 1/2, 3/4 or something like that, and the way accuracy goes up gives you some idea how far away from the real point of data you are. And typically you need more. Okay? Now, that is typically, machine learning is a lot about trying things out. Here, what Tobias looks at essentially is the question, let me get back to the slide before I show you the data, because the data is slightly complicated. So now I have a data set of many interactions. Protein A is a particular protein in human, alcohol dehydrogenase for instance, and alcohol dehydrogenase has many binding partners. And many of these binding partners are resolved very well in terms of experimental findings. As long as I do my clustering right, the question becomes, how many should I pick for ADH? 1 or many? Again, we talked about the other problems before, that there's an overlap between A and B, being the training set, yes or no, blah, blah, blah. All of these things have been considered, and this problem still remains. Could be that ADH interacts with many other proteins, and they all have not been part of the training set. So if that is the case, they're all good interactions. And that brings us back to exactly what we had before. If you had several ones, how to choose one, or should you just choose them all? Because, in fact, we have a lot of evidence that our data set is not large enough. So, clearly, the answer is we choose everything. But once again, plus means that choosing everything is a bad idea. Let's not get back into the detail of the data here. It's a complicated paper, but for many methods and many levels of the recall, essentially all for these top 3 methods here, for essentially all recall levels, by sampling more than one interactions you do damage. And these are good interactions. Why is an utter puzzle to me. This is the situation where A and B have been in the training set. Is slightly different when they have not been in the training set, but that's a detail. One thing is absolutely clear here. We cannot explain why. Okay? This is a finding. I've never in my life I have 25 years of experience in machine learning in biology, and I've never encountered a situation in which I add good data, good defined as experimentally valid, and defined as it does represent something new in the spectrum, and I have a situation in which I need more data, then I add new data and I do damage. I've never encountered anything like that, and I cannot explain it. We have a sort of sensation, or we have an idea, we have a suspicion why this is the case, but we have absolutely no understanding. What it shows is we have a situation here. What made it so complicated, the protein interaction? Simply that you now have a pair interaction. Interacting means pairs come together. In some sense you square the problem of redundancy reduction, the problem of overlap, the problem of novelty, all of that. And machine learning is extremely sensitive to that. And that brings us to the next issue, how to do it best. This issue was a long path. Tobias used the profile kernel SVM, and the new method here is this light blue, and the dark blue is the new method in a filtered way. So in a ROC curve, this clearly does better than what we have in the database before us. And that's the point where I'd like to switch off the camera.